Hello and welcome to our first lecture in Unit 2, which is all about kinetics. So kinetics is all about how reactions go from reactants to products. How do they get from point A to point B? Do they do it quickly? Do they do it slowly? What is the pathway that they take? So we're going to go into all of this as we go through Unit 2. We're going to start with simple reaction rates. So what is a rate in the first place? A rate is a measure of how any property changes over time. So think of when you're driving your car, you're driving 50 miles per hour. That's a rate. The change is in your distance, your mileage, and your time is in hours, so miles per hour. So a reaction rate is the change in the amount of reactant or product over a unit of time. So the thing that makes anything a rate is that time piece, okay? So typically for reactions, we're going to be focusing on how the concentration changes over time. So in this graph is actually showing number of molecules, but it's the exact same idea. So we notice how our reactant is going to decrease over time, and our product is going to increase over time. So brackets are used to indicate concentration. So for reaction rate, I have the change, so delta is change. The change in concentration over the change in time, or final concentration minus initial concentration, final time minus initial time. So change in concentration over the change in time. Now, if you need a little review on how we represent concentration, we use molarity. So molarity is a capital M, and it's how many moles are in a liter. So it's moles per liter. Okay, so we can even use this as a conversion factor. So how many grams are in 2 liters of 2.5 molar nitric acid? Well, I have 2 liters. In 1 liter, I have 2.5 moles, because that's what this 2.5 molar means. And in 1 mole, I have 63.01 grams, and I get 315 grams of nitric acid. So I do that to tell you that molarity is just treated like any other unit. It's moles per liter. Even though it is a per, like moles per liter, we can use molarity as a unit. Okay, so let's look at this graph. We're given concentration versus time. All right, these are the 2 variables that we're really going to be focusing on this unit. How is concentration changing over time? So the first question is, what is the initial concentration? So I'm just simply reading the graph, and at time 0, I have 0.800 molar. So that's my initial concentration. Is this a reactant or a product? Well, this is absolutely a reactant, and I can tell because it is present at the beginning and it decreases. Okay, so I can tell that this is a graph of a reactant because it is decreasing in concentration over time, but I had some present in the beginning. So now this says, what is the change in concentration over the first 10 seconds? So here is the concentration at 10 seconds. So I started at 0.8 and I am ending at 0.55. So my change in concentration is equal to 0.55 minus 0.8, which is negative 0.25. So that's my change in concentration. Now, in order to make it a rate, I have to divide it by time, so 10 seconds, and I get that my rate is 0.025 molarity per second. So over the first 10 seconds, my concentration of reactant was changing by 0.025 molar every second. All right, let's look between 60 and 70. So I go from, let's say, about 0.08 down to 0.05. 0.08 is equal to negative 0.03. And now the rate, I have to divide it by those 10 seconds. And I'm going to get, I'm running out of room, so I'm going to go down here at the bottom. I'm going to get negative 0.003 molarity per second. All right. So my rate of change for the first 10 seconds, and then my rate of change for seconds 60 to 70. So was the rate of change the same? No. The rate absolutely slowed down. The rate of change in the first 10 seconds was much faster, much higher than the rate of change in 6 times 60 to 70 seconds. Why are the numbers negative? Because the reactant concentration is decreasing. So if I do final minus initial, I get a negative number. All right. However, something to point out, rates are not negative. If I drive my car backwards at 20 miles an hour in reverse, or if I drive it forward 20 miles per hour in reverse, maybe my location change is negative when I'm going backwards and positive as I'm going forwards, but I'm not driving at negative miles per hour, right? So rates are not negative. They are not direction dependent. So technically, when you mathematically subtract a smaller number minus a bigger number, we get a negative. But all of our rates will be positive. So just keep that in mind. So now let's look at this graph. We've added another curve. Now we have this dashed line. Is it a reactant or a product? It is absolutely a product because it is not present at the beginning. And it is increasing in concentration. So now I'm going to calculate the reaction rate over the first 10 seconds. So I went from 0 to about 0.5. So about 0.5. So my final is 0.5 minus 0 equals 0.5. And now to get the rate, I'm going to divide that by 10 seconds, and I get 0.05 molarity per second. All right? And it's absolutely a positive number because my concentration is increasing. So again, this time I'm subtracting a large number minus a smaller number, so I'm absolutely mathematically going to get a positive number, and the rate is still positive. So now, in the first 10 seconds, so to right here, in the first 10 seconds, for my reactant, my rate was 0.025 molar per second. And for my product, it was 0.05. So in the previous slides, I found that the rate of change in the first 10 seconds for my reactant was 0.025, for my product was 0.05. So what is the ratio? Well, anytime we find a ratio, we divide by the smallest. So 0.05 divided by 0.025 is equal to 2. So that tells me that my rate of change for B is 2 times A, so the equation for this reaction is A yields 2B. So my ratio of my concentration changes, the rate of my concentration, gives me my coefficients. So we can kind of calculate 3 different rates. We have the average rate, which is the concentration at the beginning and end of a time period. So that's what we just did in these previous slides, was we calculated an average rate over a time. There is an instantaneous rate, which is the reaction rate at one specific time. If you've taken calculus, you know that that is the slope of the tangent line. You absolutely do not need to be able to calculate that. You will not be given a question where you have to calculate any type of slope of a tangent line. You just need to be aware of how an instantaneous rate, which is at one point in time, is different than an average rate, which is over a period of time. And then the initial rate is the instantaneous rate at time equals 0. So you just need to be aware of how those 3 different rates are different. But most of the time in these questions, you'll be given a rate. You'll be given an instantaneous rate. You don't have to calculate it. It will be given to you. So as we mentioned in the previous slides, rates can be determined as disappearance of reactants or the appearance or formation of products. So in this equation right here, we have nitrogen gas and hydrogen gas forming ammonia. So it would be the disappearance of nitrogen and the disappearance of hydrogen, or how they're used up, and then the appearance or formation of ammonia. Now remember, for reactants, the concentration is decreasing, and so mathematically that would give me a negative number. But rates are not negative, so the rate is positive. Then we have the appearance or the formation of ammonia. We don't have to worry about that sign changing because that will mathematically give me a positive number, so rate is still positive. Okay, so let's look again at how these rates are related to the coefficients of an equation. So up here, I'm given the equation that 2 ammonia decompose into a nitrogen gas and 3 hydrogen gases. And then down here in my graph, I am given the rate of disappearance of ammonia, 1.94 times 10 to the negative 6 molarity per second. And then I'm given the rate of appearance of hydrogen, which is 2.91 times 10 to the negative 6, and the rate of appearance of nitrogen, which is 9.7 times 10 to the negative 7. So those are my 3 instantaneous rates for my reactants and my products. So now I want to find their ratio. So in any ratio, I divide by the smallest. So here my smallest is nitrogen. So I divide hydrogen by nitrogen, and then I divide ammonia by nitrogen. And when I do that, I get 3 and 2. And of course, I didn't include here, but nitrogen divided by itself is, of course, 1. So think of this like when we were doing the empirical formulas. We're dividing by the smallest rate. All right, and so what that told me is my coefficients. So 3 hydrogens, 2 ammonia, and 1 nitrogen. So my coefficients tell me how my rate of reaction of formation of product or disappearance of reactant are related to each other. So the coefficients relate the rates to one another. So we call this relative rates. So comparing the rate of disappearance of the reactants or appearance of a product. We just use our stoichiometric coefficients. So if I had this generic reaction and my coefficients are these lowercase letters, if I know the rate of A I could figure out the rate of B by simply using my coefficients. A cancels out, and I'm left with the rate of B. If I'm given C, the rate of C, I can also convert it to B, even though it's a product, just by using my coefficients. C cancels, and I'm given the rate of B. So let's do an actual example of this. So I'm given the equation that ammonia plus oxygen gas yields nitrogen monoxide and water. If the rate of formation of nitrogen monoxide is 2 molar per second, what is the rate of consumption of oxygen gas? So the rate of nitrogen monoxide is 2.0 molar per second. Now look at my equation, and the coefficient for nitrogen monoxide is 4, so 4 nitrogen monoxide is to 5 oxygen gases. So I'm going to multiply 5 times 2, which of course is 10, divide by 4. And so the rate of oxygen gas is 2.5 molar per second. What is the rate of consumption of ammonia? So I'm going to start again. I have 2 molar per second for nitrogen monoxide. 4 nitrogen monoxides are produced every time 4 ammonias are consumed. So they are going to have the exact same rate, 2 molar per second, because their coefficients were the same. One more example. If the rate of decomposition of ammonia at 1,150 K is 2.1 times 10 to the negative 6 molarity per second, what is the rate of production of nitrogen and hydrogen? So this time we weren't given our equation, so we have to make sure we write our balanced equation first. So decomposition of ammonia into hydrogen and nitrogen. Okay, so now I have my balanced equation. This temperature is just given as information. It is not used to solve this problem because the rate would change if I changed the temperature. So just for clarity's sake, they go ahead and give you the temperature at which this reaction occurred at. You don't need to use that number for anything, okay? So I do know that 2.1 times 10 to the negative 6 molarity per second is my rate of decomposition of ammonia. And every time 2 ammonia molecules are used, 1 nitrogen is produced. So I'm just going to divide this number by 2, and I get 1.05 times 10 to the negative 6 molarity per second is my rate for nitrogen. And then I'm going to do the same thing . 2 ammonias are used every time 3 hydrogens are consumed. So I'm going to multiply that number, or that rate, by 3, and then I'm going to divide it by 2, and I get 3.15 times 10 to the negative 6 molarity per second, and that is for hydrogen. So what this tells me is that the rate of disappearance of ammonia is 2.1 times 10 to the negative 6. The rate of appearance of nitrogen is 1.5 times 10 to the negative 6. And the rate of appearance of hydrogen is 3.15 times 10 to the negative 6. And this makes sense because, like, think about ammonia compared to nitrogen. 2 ammonia get used up whenever 1 nitrogen is made. So it makes sense that the rate of disappearance of ammonia is double the rate of nitrogen. So remember in the previous slide how I told you they gave you that temperature for clarity's sake, because technically if the temperature changed, the rate would also change. That's because we have different factors that affect the reaction rate. One is just the chemical nature of the substance. Depending on what it was, some things are more reactive than other things. So depending on what your actual reactants are, the speed at which they react is going to differ. The physical state or the surface area. So I like to use Alka-Seltzer as an example. So if you take an Alka-Seltzer tablet and you throw it in water, it's going to dissolve and it bubbles. If you crush up that Alka-Seltzer tablet, and you put it in water, it's going to bubble way faster because you've increased the surface area. You've added places for the reaction to occur. So if I increase surface area, I'm going to increase my rate of reaction. Typically, if I change the temperature, if I increase my temperature, I'm typically going to increase my rate. If I increase my concentration, I'm going to increase my rate because the more there is, the more to react and the faster it's going to react. And then a catalyst speeds up a chemical reaction. So later in this unit, we're going to talk more about how catalysts speed up chemical reactions. But you would have talked about this in biology when you learned about enzymes and how they speed up different reactions. So we have to keep in mind all these factors that can alter the rate of a reaction.